welcome to my channel. Right here in this playlist, we will be considering IIT JEE, or what is now known as JEE Advanced exam papers. So we will solve mathematics questions, previous mathematics questions for those who may be preparing for this examination. So we'll have a look at questions one after the other, like this on mathematics majorly. Maybe sometime later we can also have a look at physics and possibly also chemistry. For now, we're starting with mathematics. Don't forget to like and subscribe. Like this video, subscribe to the channel, and turn on notifications so you don't miss out on subsequent videos on this. Okay, thank you. So let's get on this question right away. So it says, let S be equal to this set 0, 1 union 1, 2 union 3, 4, and T be equal to 0, 1, 2, 3. Now, which of the following statements is or are true? So before we answer this question, we must know that we must know the definitions or the meaning of all of these terms and symbols first. So looking at the way set S has been defined here, it has been defined using intervals. So firstly, we should clear what is meant by this interval. Okay, and in mathematics, we use these intervals to define set of real numbers or subset of real numbers. So for instance, if you have real numbers from 1 to 10, we know that we cannot possibly list all the real numbers from 1 to 10. For instance, if you want to count, say, natural numbers from 1 to 10, that is easy. You can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can list out everything. Okay. If you have a set that contains, let's say, integers, that is whole numbers, from, let's say, -10 to +5, you can do that as well because it's quite straightforward. But when we look at real numbers, we know that real numbers contain um, all rational numbers and in irrational numbers also in that interval. So we cannot possibly list all the real numbers we have in any given interval, no matter how small that interval is. So if we have even an interval from 1.5 to, let's say, 1.6, we cannot list all the real numbers within this interval because they are much. Okay, they are infinitely many, so to speak. So if we start with 1.5, what do you think is even the next real number after 1.5? You cannot tell. You might say, oh, 1.51. Before 1.51, there is 1.05. You can say, oh, there is 1.05. Before 1.05, there is 1.001, and so on and so forth. So you cannot begin to list any real numbers between one point to some other points. It is not possible. So that is why we make use of interval definitions. Okay. So basically we have two of them. Okay, that we use for two notations that we use. We have one that denotes an open interval. So if you have something like this, where we just have this parenthesis, this is an open interval. Open interval. So if I have, let's say, A comma B, this implies the set that contains all real numbers. So it contains element x, okay, where x is a real number. Okay, so this is the set of all real numbers, and at the same time, x lies between A and B. So A is strictly less than x, and x is strictly less than B. So we call this an open interval. Okay, so this is called open interval. Why is it called open? Because we cannot tell what is the highest or lowest value in this interval. We just know that it contains all real numbers between A and B. We don't know what the highest number there is. We don't know what the lowest number there is. We just know that all the numbers here are greater than A and they are less than B. For instance, then if I have the interval, let's say -2 comma -1, this means all real numbers greater than -2 but less than -1. So think about it. What is the smallest real number that is greater than -2? Fun fact, you cannot tell what that is. So you might think that is maybe minus 1.999999. No matter how many nines you count, there's still some that is less than that and still greater than -2. So that's why we call this an open interval, because we don't know what the lowest member there is precisely. We don't know what the highest member there is precisely. We just know that the lowest member there is going to be greater than -2 and the highest number is also going to be less than -1. That's all. That's why we call this open interval. Okay, so whenever you see parenthesis like this is what we mean by parenthesis. It means an open interval. Okay, so we also have notation for closed interval. You can have something like this. For instance, when you see this, we call this bracket. When you see this bracket, it means a closed interval. So for instance, this will be the set that defines that contains x, where x is a real number and x lies between a and b. But in this case, we have x is less than or equal to, okay, I mean a is less than or equal to x, which is less than or equal to b. So that means this contains all real numbers between a and b, including a and including b. So that means this interval is closed below, so to speak, by A and above, so to speak, by B. So that's why we call this, for instance, we say this is a closed interval. Okay, so that is how we define subset of real numbers in general. So that's the only way we can define subset of real numbers, except we're using definitions like this where we are explicitly stating what is contained in the real number. Okay, but if you have to define interval of real number, then we should use this interval notation because we cannot list out the elements there. Okay, so this is an open interval, this is a closed interval. You can also have an half open or half closed interval. So for instance, you can also have an interval like this. So by this definition, firstly, it means that if you have something like 1 comma 2, this contains all real numbers between 1 and 2, including 1 and including 2. So the lowest here is 1 and the highest is 2. So it is closed below by 1, closed above by 2. So this is a closed interval as it is. Alright. So we can have, as we said, an half open or half closed interval. So if you have something like this, 1 comma 2 and this, what do you think that means? That means it is closed below by 1 but open above. Okay, so that means that in this case you will have, that means you have a set x, a set that contains element x such that x is a real number and x is greater than or equal to 1 but less than 2. So it is greater than or equal to. So this bracket always applies less than, I mean greater than or equal to if it is to the left. So this simply means now any number you have here is the lower number, the one that is higher it goes is an interval from 1 to 2. We cannot write something like 2 comma 1. That is not reasonable because 2 is obviously higher than 1. Okay, so that is the idea with the use of this symbol. Okay, so this is the meaning of this set. So we can say this is half open or half closed. Can also be that the parenthesis is at this end and the square, which is the brackets in this case, is at this right end. It doesn't matter. What is important is that when you see the square bracket, you know for that end we have or equal to. And if you see the parentheses, you know for that end we have strictly less than or strictly greater than. Okay, that is that about interval. So you should now understand what this set implies. Of course, we know the union of two sets simply means the set we obtain when we put together all the elements in this in the individual sets. Okay, so that means what we are given here is the set S. So we simply say that the set S is as given. It is best we leave it that way. This contains all real numbers from 0 to 1, then all real numbers from 1 to 2, then all real numbers from 3 to 4. So let's reproduce it as a given. Real numbers from 0 to 1, union real numbers from 1 to 2, union real numbers from, what else do we have there? From 3 to 4. So real numbers from 3 to 4. So as you can see, this excludes 0, it excludes 1, excludes 2, excludes 3, excludes 4. It also doesn't include real numbers from 2 to 3. So you can see that is not included here. All right. Then we also have the set T. So the set T is here 0, 1, 2, 3. So this contains here 0, 1, 2, and 3. So in this case, this is a finite set because we can obviously just list out all the elements. So these are all the elements of the set T. In this case, this is an infinite set because even the real numbers from 0 to 1 are infinite. So we cannot list out all the real numbers from 0 to 1. So this is an infinite set. This is a finite set. Okay. So that is that about that. Then we now go ahead to look at the options. We are asked which of the following statements is or are true. That this implies that you can have more than one statement to be true. So we have to watch out for which of the statements are true and pick all of the options that are true. Okay, so it can also happen that we have just one. That's why we have is or are. This means is or are true. So we will consider the options one after the other and see which of them is true. So look at this. It says there are infinitely many functions from S to T. There are infinitely many strictly increasing functions from S to T. There are the number of continuous functions from S to T is at most 120. Every continuous function from S to T is differentiable. So everything has to do with function from S to T. So that means we should also have here a good understanding of functions. What are functions and how are functions defined from a given set to another? So let's say that, so we'll define, for instance, let f be some function from S to T. So basically, this means that S is going to be what we call the domain of the function, and T will be the codomain of the function. So what is meant by a function from S to T? It simply means we have a map or mapping that takes elements from the set S and map them to elements of the set T. So now it is not all mappings that are functions. So we have to be clear precisely what is meant by this function in this case, or by function in this case that goes from S to T. So it picks elements, as we have said, from the set S. So if this represents the set S, it's going to map elements in this set to another set, which is the set T. Okay, so this is what we mean by a function. But what makes it a function anyways? This is generally what mappings are. Mapping simply means we will associate some elements in the set S, okay, with some elements in the set T. But in the case of a function, function is a special kind of mapping. So let's have an additional page here. In the case of a function, it happens that every element in S, that is this domain, every element in S has a unique element in T. That means there is no element in S that will not have a corresponding element, or what we call an image in T. So that means that, for instance, for illustration now, if we have a map like this, let's say this is the domain and we have just A, B, C for the simplest case of mappings and functions now. and we had something like 1, 2, 3, 4. Then if we have something like this, so such that this A is associated with 1 and B is associated with 2, but C is not associated with anything. Now, because there is an element here that is not associated with anything, this is not a function. For it to be a function, every element here has to be associated with only one element here. That is what makes it a function. That is what differentiates it from other kinds of mappings. Okay, so that idea is very, very important. Okay, so if I have a function from S to T, that means that for this to be a function, it is important that so I'm writing this in capitals so that you know it is very important that every element in S must have, so every element in S must, this is a must have only one is also to be stressed. Only one image, only one image in T. Every element in S must have only one image in T. That means, in other words, every element in S must be associated with only one element in T. So, if you have an element in S that is associated with two or more elements in T, then that is no longer a function. That is not a function. It is still a mapping, but it is not a function. And if it happens that there is some element in S that does not have a corresponding element in T, or that is not associated with any element in T, then it is not a mapping. So it is not a function rather. That is some mapping, but it is not a function. So if for a function, every element in the domain must have only one image in the codomain. So this is called the domain, and this is called the domain, the set from which we are taking the element, and the set to which we are mapping is called the codomain. So that is the idea. So don't forget, it is here that we have to pick all the elements. Okay, they must be mapped to each one of them. Every one of the elements here must have one element here, at least one element here that is associated with it. Okay. Now, but the reverse is not necessary, or the converse is not necessary. That is, it is not every element in this codomain that must have an element or a corresponding pre-image in the domain. Okay, so that is not necessary. If that happens, that will give us some special kind of function. Okay, but for a function generally, this is all that is required. All right. So that definition is necessary so that we will know when we get to the other options what we have to consider before we tell whether that option is a correct statement or not. Okay, so for this A part, it says there are infinitely many functions. So it just says functions, it doesn't specify any kind of function. So that's why it's sufficient for us to just know what a function is to be able to tell if this statement is right or wrong. So it says there are infinitely many functions from S to T. Is that correct? So look at this now. In this case, we have many. We know that S is an infinite set. Okay, that the number of elements here are infinite. So this one is finite. So we have only 4 elements here. Now we now consider that, okay, what is the total number of ways by which we can associate every element in this set to some elements, only one element in this set? That is how to determine how many functions can we actually have. Now, what you should have in mind is that there is no restriction as to what element a given element in this domain is associated with in the codomain. There is no restriction to it. So we are not saying that if we pick 0, for instance, and 0 is associated with 0, it does not mean 1. Sorry, 0 is not part of this set. If we pick, say, 0.5 and we associate it with 0, yeah, 0 is part of this set. It does not stop us from associating another number, let's say 0.9, with the same 0. There is no restriction about that. So that means that every element in this set can be associated with any of these 4 elements in the set T. So that is the idea. So since there are infinitely many elements here, then we know that for all of these elements, for each of these elements, we have 4 options to pick from. So if I pick element, say 0.1, for instance, I can associate it with 0. That will be a kind of mapping. I can associate it a kind of function. I can associate it with 1. I can associate it with 2. I can associate it with 3. It doesn't matter. It doesn't change anything. I am still having a function. Even if every other element is associated with whatever they may like. Even if every other element is associated with 0 as well, it doesn't change the fact that we still have a function. So that means this first statement is true because there are infinite elements here, and each element can be associated with T or elements in T in 4 ways. For each element, we have 4 options to pick from, and now we have infinitely many elements. So that means, for instance, we have for each element now we have 4 ways, okay, to associate it with an element in this set. Now we have infinitely many elements. So normally we might say that this should be, if we have only 2 elements, we can say, okay, for the first element, we have 4 ways, okay, to actually associate it with an element here. And for the second element, we have 4 ways to associate it with an element here. And so at the end of the day, we say we have 4 by 4 times 4, which is 16 ways to actually define a function. Okay, that goes from S to T if S had only 2 elements. Okay, so what do I mean by that really? So look at this. For instance, if you had just 2 elements, let's say we had this set. This set is just A and B. It contains only A and B, and this one contains, let's say, it contains 1, 2, and 3. So I can have a set where this just goes to 1. This is associated with 1, and B is also associated. I can have a function, sorry, where both of them are associated with 1. That is correct. This is still a function. We have said that there's no restriction as to what an element here is associated with. What is important is that every element in this domain has an element associated with it in the codomain. So this is one way to define a map between this set that contains only A and B and this set that contains 1, 2, and 3. Now, if we go further, we can have another option still with the same set. So we can say that with the same set, we'll have, let's say, A, B again, and we have 1, 2, and 3. Then we associate A with 1 again, but this time around we want to associate B with 2. So this is another option. We can also have another option where A is associated with 1 still, but B is associated with 3. So in that case, we will have this AB. Okay, we still have 1, 2, 3 here. A is associated with 1, but now B is associated with 3. So altogether, these are 3 different functions possible from this set that contains only 2 elements and this set, the codomain, that contains only 3 elements. Okay, so we have 3 possibilities here. For now, when we consider that A is being mapped to 1, so that is all. That's what we can get from this case when we say that when we assume A is being mapped to 1. But we know that that is not the only option A has. A can also be mapped to 2, for instance. So if you map A to 2, then we'll have something like this, 2 and 3. So we can have this mapped to 2. If it is mapped to 2, then for B again we have different options. We can map B to 1, we can map B to 2, we can map B to 3. So altogether for this situation where A is mapped to 2, we can have up to 3 different functions. Just as we had it here, we could have up to 3 different functions here. And finally, if we now choose to map A to 3, look at it now, A is being mapped to 3, A 1, 2, 3, we map A to 3, that means A comes this way. If A comes this way, then we know for B, B can go to 1, B can go to 2, and B can go to 3. Altogether from here, we have 3 options to pick from. And that covers all possible functions that we can get using this sets here. Let's say this is some set A now that has only 2 elements, and this is some set B that has only 3 elements. So what have we seen here? We have seen that altogether we can have 9 different functions. We can have 3 functions from this arrangement, 3 functions from this arrangement, 3 functions from this arrangement, 3 plus 3, 6 plus 3, that is 9. So altogether what we have here is just 3, if you like, to the power of 2. So that is the idea. So that is that about that. So you already have an idea that if we were to develop a formula for getting the possible number of functions we can have from a combination of two sets, then it should be the codomain, the number of elements in the codomain, 3 here, raised to the power of the number of elements in the domain, raised to the power of 2. Of course, this will give us 9. You can also check that if we do that for where we have 3 elements here and 3 elements here, it will be 3 to the power of 3. So that will give us 27 if we have 3 elements here, because in that case, we'll have 3 choices here to make. Okay, we'll have 2 other choices to make here, which will further complicate the options that we have. Okay, so that is the idea when you're trying to look at how many elements are possible. So you can also see this as 3, okay, multiplied by 3. Okay, so you pick number of elements in this, then you multiply it by itself by the number of elements you have here. So that is the idea. Now look at this now. So it is quite easy now to say that because S has infinitely many elements, then if we have, as we have here now in T, 4 elements, then we should expect the number of functions that we can get going from S to T, we expect that to be 4 to the power of infinity, because the number of elements here are infinite. So of course that will give us infinity. It's like you're multiplying 4 by 4 by 4 by 4 by 4 by 4 forever. I mean, that is going to give you a number that is like forever. So there are infinitely many possibilities of the set that you can, I mean the function that you can get going from S to T. So there are infinitely many functions from S to T. This is correct. All right. So we're done with option A. Now moving on to option B. It says there are infinitely many strictly increasing functions from S to T. So in this case, we have a special term to consider. This term says strictly increasing. So we have to ask ourselves, what is the meaning of strictly increasing functions before we can answer this, before we can tell if this statement is true or not. Now let's quickly examine the meaning for strictly increasing functions. When is a function said to be strictly increasing? So that's for portion A. For portion B now, we say that a function f, so for definition, is said to be strictly increasing if f of x1 is less than f of x2 for all x1 less than x2, for all x1 less than x2. So that is the idea. So if we have a function, if we define a function and we say it is strictly increasing. The implication of strictly here is that we cannot have or equal to here. If the statement just says a function is said to be increasing, if we're looking at increasing, just increasing function, then without this use of strictly, it means then in that case that we will have something like f of x1 less than or equal to f of x2 for all x1 less than or equal to x2. So that is the idea. So, but when we say strictly increasing, that means that whenever the number we are inserting, that is the number we select from the domain, is higher in comparison to another number from the domain, then the resulting value of the function will also be higher. So that is the idea. So for instance, an example of a strictly increasing function. So you can think of an example now. For instance, if we have a function f of x equal to, let's say, x, okay, we have x plus 2, for instance. This is a strictly increasing function. Okay, so for instance, if you put in any real number here, let's say you put in 2 and then you try to define f of 2, for instance, it is going to be 2 because x is 2 here plus 2, which is 4. If you try to define f of 2.1, okay, f of 2.1, it will be 2.1 plus 2, which is 4.1. So you see that as the number you are inserting increases, the result is also increasing. So because 2 is less than 2.1, you should expect that 4, which is f of 2, okay, f of 2 should be less than f of 4.1. So that is the idea. So we're saying that f of x1 is going to be less than f of x2 for all cases where x1 is less than x2. Where in this case, okay, so we should define this more properly. We should say that a function f, okay, from A to B, from set A to set B, is said to be strictly increasing if this is this, where x1 and x2 are, of course, elements of the domain A, right? So that is the idea with strictly increasing function. So now let's get back to the options we have here and see. These are our sets now. We have this set which has infinitely many elements, and we have this set which has only 4 elements. You can see this goes from 0 to 1 to 2 to 3. Now, if we're going to define our function, now we have a restriction. We're not just defining the function, we have a restriction. That means that if we pick, for instance, look at it this way. Think about it this way. If we pick an element from this set S, let's say we pick 0.1, okay, and then we pick 0.2, and then we pick 0.3, for instance, and then we pick 0.4, and then we pick 0.5. Obviously, 0.1 is less than 0.2. 0.2 is less than 0.3, 0.3 is less than 0.4, 0.4 is less than 0.5. All of these are members of the set S. So if we will have a strictly increasing function, it must be such that f of 0.1 is less than f of 0.2, and it is less than f of 0.3, it is less than f of 0.4, less than f of 0.5. That means all of these have to be mapped to different elements. That means every element has to be mapped to a different element in T, because that is the only way it is increasing. So if 0.1 is mapped to 0, for instance, and 0.2 is also mapped to 0, that is not increasing. I mean, that is not strictly increasing. Strictly increasing that means that there is no possibility of them being equal if the numbers we are putting into the function are not equal. So that is the idea. So in this case, we can obviously see that there is no way we can define a strictly increasing function with this set S and this set T, because this contains an infinite number of elements. So there are no enough elements here to go round if we have to go strictly increasing. For instance, if f of 0.1 is 0, for the function to be strictly increasing, f of 0.2 must be higher than 0. So the option is 1, for instance. For the function to be strictly increasing, f of 0.3 has to be higher than 1. So maybe the option is 2. F of 0.4 has to be higher than 2. Maybe the option is 3. Then what will happen to f of 0.5? There is no other option to pick. What will happen to f of 0.6? No option to pick. And we still have many, infinitely many elements to pick from S that we still have to assign values that must be strictly increasing. So we can see that there is no possibility at all of having a strictly increasing function that goes from S to T. So that is to tell us that there is no doubt about the fact that this is not possible. We cannot have any strictly increasing. So the issue here is this word strictly. We cannot have any strictly increasing functions from S to T. Okay, so that is clear. Now we go to the next option. It says the number of continuous functions from S to T is at most 120, that is cannot exceed 120. Okay, so we should ask ourselves now, what is meant by a continuous function from S to T? So when do we say that a function is continuous? Okay, for layman definition, we say that a function is continuous when you don't have to lift your pen at all when you're graphing the function. Okay, so we say that generally, if we're going to give a technical definition, we say that f of x or f is continuous, okay, when the limit, okay, that's this continuity at the point now, okay, said to be continuous at a point in its domain, at said to be continuous at a point x naught. Okay, so let's say f here has a domain of A. So f is some function that maps A to B. So f is continuous at the point x naught element of A, that is at a point in its domain. If f of x naught is defined, that is it's a real number, and it is equal to the limit of f of x as x approaches x naught. So basically this implies that if you draw the graph of the function, for instance, let's say this is the function, this is our x-axis, this is y, which is f of x. Now we draw the graph of the function. Let's say the graph of the function is like this. This function is continuous. Now it means that if you come here, this is the definition of the function. When you trace this out, it will tell you the value of the function at this point. And then if you want to get the limit simply means that as x approaches a certain value, let's say x is equal to 2 here, as x approaches 2 from the right, for instance, what value does the function approach? It approaches this f of x. Okay, so basically for a continuous function, you can draw through, you can make a graph through these points where it is continuous without lifting your pen at all. So you can draw the graph through these points. Okay, you know that the function is continuous at that point. So we say that a function is continuous. We just say continuous in general without specifying a particular point now. If it is continuous at every point in its domain, okay? So when we say that f is continuous, we say that f, okay, is said to be continuous. So if I have a function, generally, it is said to be continuous if it is continuous at every point in its domain. If it is continuous at every point in its domain, at every point x naught element of A. So its domain here is A. So if it is continuous everywhere, That means that when we pick a graph of the function, everywhere the function is defined, it is going to be continuous. We don't have to lift our pen at all, except the function is not defined within that interval, then we might have to lift our pen and move to the next interval where it is defined. Okay, so that is the idea with continuous functions. All right, so now a function will not be continuous, for instance, if we have in its domain, let's say that this function goes this way and it gets here. Okay, the function has its end here, and from this point forward, it is defined at this point. Let's say this is x equal to 1, and the function is defined at this point to be, let's say, 2 here, and then from that point forward, let's say from 1, from every value that's greater than 1, the definition is now 3. That will be discontinuity because we are still in the domain of the function. Everywhere here is domain of the function, but we have to jump here from this point to this point. That is a discontinuous function. But if it happens that maybe the function is not defined here, so let's say we have something like this. The function has a domain of the function is up to this point. Maybe it does not include 1, x is equal to 1 here, but the domain of the function does not include 1. Maybe the next number after 1 is 2, and then the function continues here, and then it goes on like that. Maybe it is not even defined at 2, but it's defined as numbers that are greater than 2, and then it stays continuous like that. So we still regard that function as a continuous function, because in that case, if it is not defined here, since it is not defined here, that means we know the function does not have this portion to be part of its domain. So because this portion is not part of its domain, we will say that the function is still defined everywhere in its domain. So sorry, it is still continuous everywhere it is in its domain, at every point in its domain. So this is part of the domain of the function. This is part of the domain of the function. We still regard this function as a continuous, even though it is discontinuous here. But where it is discontinuous is where the function is not defined. So it is discontinuous only where the function does not have, the function is not defined, that is, those values of x that are not part of its domain normally. All right, so that is the idea with discontinuity. Okay, so I'll link a video to this so that you can learn more about continuity and discontinuity. Okay, um, so that is that about that. So now let's get back to the problem statement. It says the number of continuous functions from S to T is at most 20. So we should ask ourselves now, if the function is going to be continuous, what are the options we have? How many ways can we define this function so that it is continuous from S to T? So we will now examine again the set that we were given. We're given this set 0, 1. So let's write it out again: 0 to 1, 1 to 2, and 3 to 4. So let's write that set out again. We have the set S here, which is 0, 1, union 1, 2, union 3, 4. And then we have the set T, which is equal to 0, 1, 2, and 3. So if we want to define a continuous function now from x to t, what are the options that we have? It has to be continuous, don't forget. Now this set is not continuous, so to speak, in the sense that this one just goes from 0 to 1 to 2 to 3. It doesn't contain everything between 0 and 1, or everything between, by everything I mean all real numbers between 0 and 1, or all real numbers between 1 and 2. So for instance, if we were to say I have a graph of this function, or the function that we can possibly form from here, we know that this one can only go from 0, it can only have values 0, 1, 2, and 3. So the output, that means our f of x is restricted to the values 0, it can only be 0, okay, or 1, or 2, or 3. It cannot be any other value between, it cannot hold any other value here. So we cannot have a function that goes like this, that the graph will go like this. For if it goes this way, that means at some point here, the value of the function will be 2.3, but that is not part of the codomain. So the function cannot have any value that lies outside 0, 1, 2, and 3. So that tells you something, that if the function we form here is going to be continuous, it cannot be something that goes continuously from one number to the other, because anyhow it goes from one number to the other, it will not be restricted to this set as its codomain. So because it has to pick from this set as its codomain, then the only continuity we can have here can only be a case where maybe the function is defined here and it's just a horizontal line like this. And then from some point forward, it is also another horizontal line that is on 2. Then from some point forward, it's also another horizontal line that is on 1. Then from some point forward, let's say it is also another horizontal line that is on 0. That is the only way we can have any continuous function, okay, that goes from S to T, because T is restricted to being 0, either 0 or 1 or 2 or 3. We cannot have any other option for this, okay. So that is the idea with continuity. So it can only be some continuity by a horizontal line, okay, horizontal line definition. The line cannot go from one point, like go continuously from one point to the other. That's because that would require that it takes on values that lie between 3 and 2, which are not part of this set. Okay, so our f of s is restricted to 0, 1, 2, and 3. So this is an option, okay, for continuity of this function, okay, that goes from S to T. Another option that we can have, of course, we are not going to list out all the options. Another option we can have is that we can have something like this. This is still our x-axis. This is still our f of x, which can only be either 0 or 1 or 2 or 3. It can also happen that everywhere, let's say between 0 and 1, the function is 3. Between 1 and 2, the function is still 3. Between 3 and 4, the function is still 3. That is possible as well. We still say the function is continuous because everywhere it is defined, it is continuous. So we have to draw a continuous straight line. There is no break at any point. So that is an option as well. So that means for continuity, it has to be that for every continuous interval, we can only have one value for that continuous interval. So if we pick this, we know this is a continuous interval. This is an interval from 0 to 1. It covers all real numbers from 0 to 1. So it has to be that all of this, every element in this particular interval or subset of S is, let's say, is mapped to 0 or mapped to 1 or mapped to 2 or mapped to 3. That means every interval has 4 options to pick from. We cannot have any two elements here that will be mapped to two different things, because the moment that happens, there's going to be discontinuity. For instance, if 0.1 is mapped to 0 and 0.2 is mapped to 2, then there will be a disconnect somewhere, because it means there has to be a jump even within the interval where the function is defined. So for instance, if 0.1 is here and it is mapped to 0, that means the function will be defined here. If the next number, let's say 0.2, that is close to it, is mapped to 1, that means the function will now be defined here. Then it is no longer going to be continuous somewhere around this. So that is the idea. So for continuity to be maintained, it has to be such that every continuous interval here is mapped to only one of these numbers. So it's either 0.1 takes on 1, or it takes on 0, or it takes on 2, or it takes on 3. That is, every number from 0 to 1 should take on just one of these. So they will be mapped to the same thing. So if every number here is mapped to 0 or 1 or 2 or 3, it does not stop every number in this subset to also be mapped to any number it likes. So they can be mapped to the same thing. That's why I would draw out this option. So that means that for every subset here in the set S, we have 4 options to pick from for a continuous function to be defined. So there is no restriction. It can happen that this one is mapped to 0 and this one is also mapped to 0 and this one is also mapped to 0. There is still continuity. It can happen that this one is mapped to 1 and this one is mapped to 1 and this one is also mapped to 1. There is still continuity. So there is no restriction. So this can pick on any 4. This also can pick on any 4, and this also can pick on any 4. But it has to be that whatever we have in this interval, the definition or definition of f for every element in this interval has to be the same. So that's what's important. So altogether, how many ways can we define that function? It means in this case, you can see this as though we have the domain to have only 3 elements, but of course we know they are not 3 elements. In this case, they are just 3 intervals. So we're saying that each interval can be mapped to only one element. Okay, they should have the same image. Every element in a single interval should have the same image. So it's as though we have 3 elements in the domain, and then as usual we have 4 elements in the codomain. So we should expect this to be 4 to the power of 3 ways by which the continuous functions can be formed that will go from S to T. Or if you like, say if this can choose, or if an image can be chosen for all the elements in these intervals in 4 ways, and an image can be chosen for all the elements in this interval in 4 ways, and an element can be chosen for all the elements in this interval. An image can be chosen for all the elements in this interval in 4 ways. Then altogether we have 4 times 4 times 4, which is still 4 to the power of 3 ways of forming continuous functions that go from S to T. So that means we have 64 options altogether. 4 to the power of 3, that's 4 times 4 times 4, that's 64. So we have 64 options of continuous functions that we can form from S to T. So that is the idea. And now look at the option. The option says the number of continuous functions from S to T is at most 120. Oh, think about that now. We just said the highest that we can have, or all the numbers of continuous functions that we can have that go from S to T is 64. And this statement says at most 120. Can we say 64 is at most 120, or something that is 64? Can we say it satisfies the condition of at most 120? At most 120 simply means it cannot exceed 120. And indeed, anything that has to be 64 cannot exceed 120. So this statement is correct. Okay, at most 120 simply means it cannot exceed 120. Of course, we know it is 64, and of course 64 cannot exceed 120. So that is that about that. There are 64 possible continuous functions that we can have that go from S to T. Okay, and 64 is not exceeding 120. So this is simply saying the number of continuous functions that go from S to T does not exceed 120. Yes, that is true. So this statement C is true, therefore. Now, the last part. It says every continuous function from S to T is differentiable. What is meant by differentiability? So we should ask ourselves that now. What do we mean by the differentiability of a function? Okay, again, I'll link a video or some videos to this so that you can have a more robust understanding of differentiability. But what do we really need to know here? Let's quickly discuss that so that we can answer the question. And right, so we have every continuous function. So we have seen the possibilities of continuous function, all possibilities of continuous functions, so to speak, that we can get. Okay, going from S to T. So we now ask ourselves, considering all of these possibilities, are all of these functions going to be differentiable? Differentiability simply means will the lines or sections or curves representing the function or defining the function have definite slopes. So that is the simplest way or the layman way to look at differentiability. So a function will generally be differentiable if it does not have any sharp edge, so to speak, in its graph. Sharp edge like this. If you draw a graph of a function and the graph is like this, for instance, at this sharp corner, so to speak, then there is no derivative because at this point, this sharp edge or vertex, if you like, if this were some geometric shape, you say this is a vertex. At this sharp edge, we cannot tell what the slope is for the curve because if you look at this point, and we tell if we're coming from the right, we will have to go with the slope of this line, which is going to be negative. If we're coming from the left, we have to go with the slope of this one, which is positive. So at the end of the day, we cannot tell what the slope is at this particular point. So the function will not be differentiable at this point. That is the simplest way to look at differentiability. But everywhere that the function is smooth, there is no such edge or whatever or something like that, then we are certain that the function is differentiable. If you have something like this and going this way, there is no sharp edge, then the function is differentiable. In this case, where it turns, we know that the worst case it can have here is that the function will have a zero derivative. Okay, so that is that about that. So we can have a function that has zero slope or slope of zero, for instance, which is what happens in the case of a horizontal line. So we have seen that all possibilities we can have for continuity here are horizontal line representations in the different parts. So if they are all horizontal lines, then we know that they are all differentiable. All horizontal lines are differentiable because they will have slope of zero. So you can think of horizontal line this way. This, for instance, simply means if you're going to pick this portion, for instance, you are going to have something like f of x to be equal to 3. If f of x is equal to 3, that is a constant, then we know that 3 is differentiable. Derivative of f of x is just going to be 0 because derivative of any constant is 0. So if you have a horizontal line graph, it is differentiable. Its derivative is simply 0. So that is the simplest way you should think of differentiability here. Of course, there is more complex or technical definition of differentiability you might want to also examine, okay, in case you come across questions that will require that. And as I said, I will link some videos to this so you can watch and learn more about differentiability. But this simple layman understanding of differentiability is sufficient to answer this question, that indeed, because all the possibilities or all possibilities of continuous functions that we see with the sets s and t, that is functions going from s to t, are functions with horizontal lines or horizontal line representations or different segments. They can be in different segments, they can be at different levels, they can be at the same level or whatever, but we know they are all horizontal lines and each of them will have derivative of 0 or slope of 0 because they are horizontal lines. So because of that, all of the continuous functions we can have would be differentiable. So differentiability here also follows from the fact that if a function is differentiable, it means that it is differentiable at every point in its domain. That is, everywhere it is defined, the function is differentiable. So the same idea with continuity, that if the function is continuous everywhere it is defined, that is everywhere in its domain, then the function is continuous. In the same manner, if a function is differentiable everywhere it is defined, or everywhere in its domain, we say the function is differentiable. So in this case, we know that everywhere in its domain where it is continuous is represented by a continuous horizontal line, and that is having a zero slope. That means the function is differentiable everywhere it is continuous. Okay, so every continuous function from s to t is indeed differentiable. So that is that about that. So what are the correct options here? Correct options here are therefore options A, option C, and option D. So as the instruction implies, you will have to pick all of these options, these three options. So that is that about that for this question. So in the next video, we're going to look at the next question, which is question 2. Watch out for that. Don't forget to like this video. If you find this helpful, like this video and share with your friends that may also be preparing for the same exam. And also subscribe to the channel and turn on notifications so that you don't miss out on the next video. Thank you for watching. I'll see you in the next one.